And or I can send you audio file of sons singing.
What show?
so
we ran the fluids on
oh,
that
yes,
music.
yes,
What?
yeah, that's right.
On the
Sun's music.
But our work doesn't cover that right now. So yeah.
So this sun is there, corona is there, then chromosphere is there.
And then the water starts dancing on it and it's attractive to the female alligators.
Wow.
It's attractive to us also, scientifically.
Hello and welcome to Friendship with Science, video series about doing friendship with science. And because science is abstract, we're trying to do friendship with scientists. And for that purpose, I have with me a person who has been claiming to be a scientist for a long time, Dr. Professor Shashi Thutupalli. Is correct?
Yeah.
Yes. Every time I get his name wrong. We are, of course, shooting at Azim Premji University at their beautiful campus, and thanks to them, we have this beautiful studio to shoot. This is a very interesting episode because it combines two apparently disconnected things in a very interesting way. But before we get there, friends, first like, share, subscribe. That said, Shashi will take it from here. Dr. Shashi, will you take it from here?
I will take it from here. Maybe just a couple of words about our series because, so a lot of interesting science is happening, of course, around the world, but a lot of exciting things happening in India. So we thought that this would be an interesting forum to talk about that. And so today we have two proponents of this aspect. As our guests, Murthy and Piyali, and we're going to discuss with them, like you said, this very interesting story that combines completely disparate aspects of the world. Okay, so our guest today, so Piyali is a professor at the Indian Institute of Astrophysics. Murthy is a professor here in physics at Azim Premji University. And both of them did their PhDs at the local Indian Institute of Science in Bangalore. Murthy in condensed matter physics, working on semiconductors, electronics, and so on. And Piyali in astrophysics. Yeah. And subsequent to that, both of them were postdocs in Scandinavia, Stockholm, and Norway, and also spent some time in the US. Some very interesting tales about combining movie making and science and physics and so on. But after all those experiences, now they're back here in Bangalore doing some very interesting science. And today, I guess, we're going to talk about one of Piyali's deep interests, the sun.
The sun, yes.
Okay, so...
What is the sun? We'll start from there.
Yeah, the sun is, of course, a dumb answer or nearest star. So it's a very average star in a very average place in the galaxy. Nothing exciting about it. Yeah, so...
Thankfully.
Well, the only thing that makes the sun exciting is the magnetic field.
That's the only thing that...
Well, for solar physicists.
For the solar
physicists, yeah. And of course, now we have to worry about it because, the magnetic field is something that connects the sun to the earth, the sun-earth connection, threads, strings connecting the sun to the earth. And that affects the space weather. And space weather is something we all have to worry about because we have a lot of assets in space. And we are dependent on technology or GPS and things like that. Everything will malfunction if you have solar storms and things like that. So, so the sun drives the space weather. Sun also drives the climate on Earth. But, you realize about the space weather when you have a very advanced civilization. Otherwise, you really don't. Now, the Earth also has a magnetic field, even though it's much more weaker than that of the sun. But the reason the Earth is able to hold on to its atmosphere and we have life is because we have the magnetic field. That is like a cocoon, which is basically, preserving all the
Is it
life.
not gravity that's holding it?
The gravity is, yes, of course there is. But if there was no magnetic field around the Earth, then you may have heard about the solar wind. So there is this constant breeze that is emanating from the sun into the space around it, known as the heliosphere, the solar system essentially, the space around the helios, the sun. So this wind basically is always impinging onto the Earth's atmosphere, right? And this contains a lot of charged particles and things like that, and that would evaporate the Earth's atmosphere. So the wind is constantly impinging on the Earth's atmosphere, and if there was no magnetic field, then the atmosphere would just, fly off.
So it's not
Get
the heat,
ionized.
it's the particles that are coming from the sun.
The particles.
And the Earth's magnetic thing is like a kavach.
As a kavach, which is protecting the atmosphere. Of course, there's gravity to, that's the reason you have this stratification, denser air, and if you go higher up, there is less air. That is because of the gravity. However, the fact that we still have this air to breathe is because of this magnetic field. So Mars, for example, doesn't have magnetic field. It also doesn't have an atmosphere. The moon doesn't have a magnetic field. It doesn't have an atmosphere.
Sorry, this is very interesting. So Mars doesn't have magnetic field. Is it because
It probably did a long time ago. We don't know what happened. That is that's probably another story. But the Mars doesn't have a magnetic field like Earth.
Is it because the core is not made of metal, or what is the issue?
So they believe that, the core is metal, but then to generate this magnetic field, you need liquid iron, liquid metal cores or outer cores. So maybe at some point in time, the core probably froze or solidified or whatever. So some planets don't have a dynamo. So don't generate magnetic fields in their core. Earth generates its own magnetic field, because it has a liquid
It's a
iron
dynamo,
outer core. The inner core is solid, but
Maybe
the
because
outer
it is
core
chikku,
is...
chotu.
The Mars is much smaller than the size of the Earth.
Sorry, you mentioned one more thing. Space weather. So that's not the weather, right? The weather we know is this is the weather.
This is
Bangalore
the
weather is
This
nice.
is the weather. The space weather is again this, how much of energetic particles you have, these high energy particles, which are actually traveling out at, say, super relativistic speeds. And how many of them are there? What is the temperature? What is their velocity? So these things are what governs the parameters of the space weather. Essentially, the weather, these quantities in the geospace, in the space around the Earth. Is what
Space weather
governs
is for the space guys,
the space guys.
not us. Right?
Well, not true. For example, in 1859, there was this very famous Carrington flare, right? So, which was
Canada.
No, not Canada.
The grid collapsed.
The Greenwich, the telegraph grid collapsed. The telegraph grid.
What
There
is
were
it? I have no
telegraph
idea of
lines.
this incident. Actually.
Yeah, it's interesting.
What is
So this flare is probably a flare. We haven't seen such strong flares for a while now, and if
And
such
when
a
you're
flare,
saying flare, we mean a solar flare.
a solar flare,
A solar
flare.
Yeah.
A solar flare, and it was so strong
Okay.
that it could be seen. It was recorded by naked eye.
Okay.
It could be seen in naked eye.
Okay.
And it was actually recorded by a scientist, an English scientist known as Richard Carrington in Greenwich Observatory. So at that time, people used to draw sketches. So there's this famous sketch of the sunspot from which that flare happened and how that flare looked like. So there are all these drawings available. And the aftermath was this collapse of telegraph lines. So basically the telegraph turned really erratic, right? That was some means of communication, right?
But also 80s, 84 or so, there's a
89, I think, 1989. Electrical grid in Canada, a small city known as Quebec. So the electrical grid collapsed because of, again, a solar flare. So,
It's not just for the space guys.
Yeah. It's not just for the space
solar
guys.
flare, it's so from what we know, sun is converting hydrogen into helium or helium into hydrogen, one of those things I've forgotten now, whatever it is doing. But it's like a big nuclear reactor, right?
Yeah, yeah.
And
Can it convert hydrogen into helium?
I don't know, under that much
Yeah,
pressure,
well,
it
something.
can, no?
Good. No, I just want to. Yeah, I just want to.
Can it?
Yeah.
What?
It does. It
It's a
does.
fusion
Fusion.
reaction.
Fusion.
It's a fusion reaction.
Okay, okay. Yo, why are you testing me? I don't know. I'm just asking. Sorry. So, the sun is, from what we know, rudimentary. Sun is like a nuclear reactor that is doing this, and we get heat from that. So photons are coming, and some heat is coming. I don't know if
Right.
photons are bringing the heat, but heat is coming.
Right.
But this flare is what? What is? Sorry, say.
Can photons bring it? No, just
Photons can't bring it. Can photons bring heat?
Yeah, infrared is that's photons.
Oh,
Yeah,
it
yeah.
is.
Yeah,
Yes.
of course.
Photons can bring heat.
Yeah, radiation is electromagnetic radiation.
electromagnetic radiation.
You're right all the time.
Then thermodynamics is
Bring or heat. They can heat things.
They can heat
They can heat
anything.
things,
Right? It's a
right.
it's an electromagnetic
Radiation.
Wow. Wow. Okay. I never thought photons are bringing heat, but they are. That's good. Sorry, but I was saying the flare contains photons, or it contains something else also.
Okay, so it contains the flare is when a flare happens. So it's basically like a pressure cooker, So it's like you build up things or volcanic eruption. So you build up things and there's a sudden release, very slow build up and sudden release. It's like, you suddenly, you get angry and then you get triggered. So it's the same thing. So the sun gets angry, the magnetic fields gets twisted, and then they can't contain anymore. So they just relax and then there's a flare. But when there is a flare, lot of this magnetic energy that is stored in the magnetic fields is actually converted into light, electromagnetic radiation, and they're also converted to high energy particles.
Okay.
So by electromagnetic radiation, I mean they will emit microwave up to X-rays and gamma rays. So the entire electromagnetic spectrum. So, and then there are these high energetic particles, mainly protons and alpha particles and things like that, which are also ejected. And these are the high, these particles would, so there are solar storms and the sun is a ball, so these can happen in any direction. And if you are unfortunate, then the earth is in the way. Right? And for example, you have a space station. So, the astronomers on the space station have to be careful because that's when they're getting all those radiation, the high energy radiation, which is, which causes mutation and things like that. Yeah. So people make these shields to, so that the astronomers who are working in the space station are safe.
Wow.
So these are,
Got it. So solar flares are there.
So the sun is giving us energy to, everything, the life is being run by the solar energy, but there are these side effects as well that, an advanced civilization has to be able to predict. So that is basically the crux of this predicting space weather.
Wow.
Right. So these solar flares, I guess, are constantly happening on the
No.
or no.
The wind is constantly
The
happening.
wind is constant.
Flares are
Sudden.
Flares are like storms. So the storms are not as frequent as the wind itself.
I see.
It's just like on Earth, right?
No, when I say constantly happening, I mean at different intensities, different scale.
Con-
Because it is perhaps a turbulent.
Yes, but it is also modulated by the 11-year sunspot cycle, if you have heard about it. So there are these sunspots, right? You may have heard that the disk is covered with sunspots. And the number of sunspots, it is modulated. It changes from, maxima to minima, and the cycle, like a sine wave. The periodicity is 11 years. So then the flares are more, there are more flares when there are more spots. And less when there are less spots. So that is the modulation. But yeah, it's not that during solar minimum. So right now we are entering a solar maximum. Actually, maybe 2025 we expect the sun is going to be more active than it was, say, 5 years ago.
Active in this sense.
Active in the sense that churning out more sunspots and more flares. Yeah.
So in Hindi, people say Chand pe bhi daag. I think Suraj pe bhi daag.
Suraj Pevi.
Got it. Sorry, I have one question. Why you study the sun? Like you had so many fields, like when you were studying, and then why you were attracted to the sun? I'm genuinely interested.
I started studying the sun because, I was in IAC, and then we had a very small astrophysics department at that time, and we had this person who worked on plasma astrophysics. So I was sort of, attracted to this terminology. Some terms, they look very fascinating, and I thought there would be a lot of mathematics to do here, or I wanted to do that. So that's how I ended up doing this. But yeah, I'm glad that I chose this field, because after all, most of the matter in the universe is made of plasma.
I see.
Right? And the sun is our nearest plasma laboratory. That's where, we can test our theories and...
So the interest is perhaps more driven by aspects of studying states of matter
states of
rather
matter,
than
yeah.
the sun as some astronomical
Yeah,
object
when I
itself.
started, I did not think that way. I mean, the usefulness of it.
But at the same time, you
We were
overlapped.
contemporaries, yes.
You were
Yes,
contemporary.
In
yeah.
fact, batchmates.
Batchmates.
You were
Yeah,
bachelor,
yeah.
but you were doing
Completely
material
different.
science still.
Yes, yes.
But not.
Yeah, I was grounded.
Very
Meaning,
grounded.
I was much more earthly kind of things to worry about. So I chose solid state physics, experimental physics. And I was fascinated with building instruments and measurements and all that, and going to very low temperatures like liquefy helium and those kind of things. And I also was quite interested in finding out how these electronics stuff work, what the physics behind these devices is. And I joined a person, my advisor, who was a semiconductor physicist. And I started building stuff and also looked for a problem for a while. And at that young age, you can't really find a PhD research problem on your own, which I failed. I went and I just took a material that had come in, a project, which is a defense project at that time. And we did some nice physics with it. And on the way, I built a lot of skills that were useful that I thought would be useful in many areas. My imagination was my PhD training would be in such a manner that I should be able to understand anything that any expert in a field at my level would be talking to me about. And I had a lot of frustration in the beginning because I couldn't understand much of this when I attended talks and stuff. So during the PhD, I did my research problem, but worried more about everything else that was happening around me or the skills that I wanted to build. So my journey was quite different. And it just happened to be some 50, 60-year-old material. There's not much scope to publish. So
No, but even
Ended up
now,
with a
I mean,
whimper.
I mean, those materials are this infrared
yeah, they're
detectors.
defense-wise very important and interesting. The problem is with defense kind of stuff when you're working, there's not much scope to publish because and not much literature also to fall back on or depend on because everything is like it's a secretive society, secretive societies.
Yes.
So I struck nice collaborations with American groups, and that was we were coming after Pokhran and stuff, right? So it was very difficult to talk to people, and we managed to have a collaboration around that time. So it was good. I liked designing and instruments and experiments and stuff like that. So, which is something that I do. One of my favorite labs is my kitchen. So.
No, in fact, the Hall effect that you worked on is something which is also relevant to the solar
Yes,
physics.
in
So
fact,
there are a lot of equations which are similar in the condensed matter, like metals and electrons.
Yes, that's true.
And what happens in the solar plasma.
Because both of them are like gases, and in some sense, solids also have electron gases and stuff inside. And there also we have gas, which is like plasma, and your charged particles moving in magnetic field. So it's similar kind of thing, just looks very different from these two
I have one
perspectives.
question. This plasma thing, just one question, okay? It might be the dumbest question in the world. Plasma TV and solar plasma, same plasma or different plasma?
Same plasma.
Plasma is the same.
Plasma is a state of matter.
Okay, so
Ionized.
plasma TV is generally
Plasma TV is literally that same state of matter that the sun finds itself in, perhaps not at same
Well, not at that
temperatures,
yeah.
not at the same temperature.
In fact, if you put a piece of, don't do that.
Don't do that.
Don't try this at home. Disclaimer. But you can get it in a microwave oven also.
What?
Yes.
How? Tell us.
I mean, you've
Am
seen
I-
the have you ever
Microwave
seen
plasmas
Is it
are
safe
like
to
really,
glow?
yeah.
Is it safe?
I have.
Is it safe
Or
to
if you
mention?
put
Yeah.
metal inside the
by
microwave.
mistake.
Not
Okay,
metal,
please.
you can put graphite or something to be safe, a little safer.
Guys, please
than
don't do this.
Yes.
Guys, please don't do this. Microwave will explode. You'll die. We'll cut this out.
Yeah. We should not.
There's pencil graphite.
Yeah.
Right?
You get
We'll cut
graphite
this
sheets
out.
also.
Yeah. We have to
we
cut
can't.
this out.
Okay, great. So we'll just fast forward through this. Okay, please keep a note. Sorry, coming back, we want to give safe example of plasma. So,
No,
Plasma
but
TV.
yeah, plasma.
It's
It's
the
the same plasma in plasma TV, and
got it.
yeah.
Got it. So
By same we mean the state of matter, right? It's like saying water is a liquid, milk is a suspension, but what's a pure liquid? Liquid hydrogen is liquid helium is a liquid, so they're
got
both
it.
liquids.
I get that. Oh, that
For
I
example,
understand.
plasma is used for air purification also.
Yeah.
Same
And in fact, you don't even need to go there. On a metal, you see plasma kind of thing. The electrons behave the same as they behave in this plasma, as in sun kind of plasma.
But it just seems like plasma is a cloud of electrons. Is it that? Is just that?
Cloud of charged particles.
Charged
yes.
particles.
Then why is it matter? It's not matter. No, it's just electrons. Why are you calling it state
What do you
of
mean
matter?
by
Electron
matter?
is considered matter.
right?
Oh, electron is. Okay.
It's not energy, it's matter.
So it's protonless
Yeah.
matter.
Well, it's any charged
charged
collection of
Anything that has mass and charge.
No, in the
Is that
sun you have
floating?
protons and electrons.
electrons.
So,
So
that
it's
is
not
also
simply
plasma.
protons or simply electrons. It's some ionized.
Okay, I got it. So you can have gaseous water, which is vapor. You
Yes.
can have water.
Yes.
You can have ice.
Yes.
But you can't have water plasma.
Water plasma.
Water.
Well, if you
After
take
vapor, and you ionize the vapor, you'll get
Ionizing vapor is still H2O.
you are taking one electron out or putting more electrons or something like that to make it charged. Otherwise, it will be neutral. So, if you charge them, the water molecules, the H2O molecules in water vapor, it will be plasma.
Okay. But you're adding extra electrons.
You could.
or you could heat, for example. By heating,
Dissociate.
you dissociate.
Yes.
Okay.
So then also they'll come apart.
Then also you come up. Yeah.
Got it. And the flares carry some of this plasma?
They carry some of this plasma, the proton, electron plasma, whatever the sun is made up of, in form of magnetic clouds. So sometimes these flares, so there are flares and there are what is known as coronal mass ejections. So they are basically these magnetic clouds which are being, thrown into the heliosphere, and they might reach the Earth. And then they cause auroras when they hit the Earth's magnetosphere. They break the magnetic field lines and reconnect them. So a lot of making and breaking happens, cut paste kind of thing. And then those particles, they enter the Earth's atmosphere through the poles. So that's why you see those colors, right? Green, purple, orange there, because they're interacting with oxygen molecules or nitrogen molecules and things like that. You see auroras because of that.
Yeah, the northern lights.
Northern lights, yeah.
But your work is on spicules.
Yeah.
So what is now? Flare is there.
So now we have to go from the angry side of the sun to the quiet side. So we also have to study the quiet side because he mentioned solar wind, right? So which is a constant thing, a constant flow of plasma out of the sun. And because of this, the sun is also gradually losing mass because something is escaping, right? And also it is losing what is known as angular momentum, which basically means that the sun spins, right? So right now, for example, the sun spins once every 25 to 28 days. on an average. Huh? But when the sun was young, it was spinning much faster, because it had a lot more angular momentum. So now that thing is, the angular momentum is being lost through the wind, so it is gradually spinning down, slowing down. So as the sun ages, it will slow down because it is losing that angular momentum. And what is the origin of the solar wind? So now one of the theories in solar physics is that there are these millions of jets covering the solar atmosphere. So the disk that you see every morning, the sun rising, the disk is the photosphere. So that is the visible disk of the sun. And above that photosphere is what is known as the chromosphere. And then you have the corona of the sun. The corona of the sun is the thing that you see during a total solar eclipse. Without the total solar eclipse, you cannot see the solar corona.
So corona is basically crown, right?
Is a crown of the sun. So now between this visible surface and the corona is this very thin layer known as the chromosphere. And during a total solar eclipse, when the disk is completely covered, if you try looking at this chromosphere appears red because of presence of helium. So helium was first discovered actually in the spectral line from the sun's chromosphere during a total solar eclipse. So this in this chromosphere there are these millions of jets, and they're happening all the time. They're just rising, falling, and if you take a picture of it, and it will look like a grassland where it's swaying and doing all sorts of things. And these spicules are believed to be conduits, pipes through which the sun is transferring some mass as well as momentum to the solar wind. So that's why it is important to know the origin of these spicules. And that's what we sort of embarked on initially.
Just so that I have the picture right. So you invoke this picture of a grassland. Each blade of grass is a spicule.
Is a spicule.
Okay. And the corona is there, then the red is the helium. How does this fit into that? I missed the part, like the corona.
Okay, so there's the visible disk. Yeah. And during a total solar eclipse, the moon covers the visible disk, but it doesn't cover the chromosphere, which is a very thin layer just outside the photosphere.
Right.
Chroma means color, right? Because it appears red. And then outside this thin chromosphere is the corona of the sun.
Right.
And which is basically very hot. The temperature is about 1,000,000 degrees in the corona. And it is totally charged. The hydrogen atom doesn't exist as an atom. It exists as protons and electrons and a mixture of that. So it's totally plasma there, right? And it's very thin compared to. So if I give you a feel for it, for example, water. Water has a density, right? So you know what is the density of water. So the density at the photosphere, for example, is 10 million times less than that.
Okay.
The density of the plasma at the visible surface is 10 million times less than that of the water. And in the corona, it is, say, 1,000 million. So what do you call that? Giga, 10 raised to 9.
Billion.
10 raised to giga, times less than the density of water. So it's that less dense. And that regime, it gives rise to very interesting physics. But our work doesn't cover that right now. So,
Got it. So this sun is there, corona is there, then chromosphere is there. Spicules are where? On the surface?
Okay. There's the photosphere, there's a chromosphere. The spicules are in the chromosphere.
Then the chromosphere. The red layer that you see when the helium.
Yeah.
Got it. Yeah. Okay, understood. Spicules are there. Sorry, one more question. We are told not to directly look at the sun. How do you study? Do you directly look at it?
No.
Take photos? How do you do it?
You would never do that. So you would use different filters, of course. So even in a telescope, of course, when the telescope and the light is entering, so it's not that an astronomer is sitting at the end of it looking through it. We basically detect it using CCDs. So he will know more about CCDs and CMOS. Nowadays, people use CMOS detectors. So,
But if you want to
yeah.
study the photosphere, the bright part of that, then also you'll have to cut down the light heavily. Then only you'll be able to see any structure. Otherwise, it'll just look like some white blob.
Totally washed out.
Washed out
You
thing.
saturate.
It'll saturate the sensors also. So that's why the chromosphere or the corona are best studied during eclipses, right?
Eclipses, or you use this sort of coronagraphs.
Which is basically mask the photosphere, block it, and then you will
Insta
see it.
filters.
No filter, just block it, opaque.
Just opaque. So, for example, Aditya L1 has a coronagraph. Our Aditya L1 that was launched.
So it's
in
like a artificial
September.
eclipse.
It is an artificial eclipse.
Wow. What is this?
Because you cannot have an eclipse every time. The
Yeah.
eclipse has a schedule, but you can just put a disk and obscure the
Occult.
occult. Yeah, it's an occulter.
Got it. Now the spicules you are studying, they're the object of your study, right? And then something interesting happened, and you found some connections. So how did that happen? Like, how did you get to the paper, basically, which is very interesting. How does paint come into this? And also, apparently, alligator matings are part of this. So I'm very curious what scientists are doing these days. So how does paint come into this?
Yeah, why don't you?
Okay. From my side, the story that I know of is I came back home after work one day, and Piyali, who does numerical simulations and does these nice pictures, colorful things, doing dynamics on the screen all the time.
Animations.
Animations.
Sorry, just to interrupt you there, when you're saying numerical simulations, you're trying to simulate
Yes.
the
Yeah,
formation
yeah.
of these spicules.
By solving some set of equations.
Yeah, physics
So
equations.
these are
Equations.
basically some plasma.
Yeah, these are basically fluid equations,
Fluid equations.
like people do in CFD and things
Exactly.
like that.
I just wanted
But
to
we add magnetic field to
Sure.
it.
These are magnetohydrodynamics.
Magnetohydrodynamics.
Yes. So this fluid
Exactly,
dynamics plus this charged particles electricity magnetism. So when I came back, I was on the screen, something was happening, and she said, she opened a YouTube video and asked me what it was. So I could see that there's paint. There's YouTube channels, the science popularizers, with who put paint and on a speaker and then put some bass music, and then there's nice stuff happening. The interesting thing is it looks mesmerizing when you look at it in slow motion. So I looked at it, and so I said, what about it? So he said, so I showed it to our daughter. Both married.
You didn't pick it up, right?
I didn't pick it up. So she said,
So you're just showing him the simulation and this video.
No, I didn't show any
not simulation. I knew that.
Oh, you
simulation.
knew the
Because,
simulation.
No escape in the family.
No, because I used to discuss with him. So yeah.
So she said, I showed it to our daughter, and daughter asked her what it was like, and she said, they look like your spicules. And that was very striking, and both of us, being a little trained, caught on it, because there's this nice visual similarity. Because when you mentioned grass is permanent kind of thing. In spicules, basically the plasma is rising and then falling back mostly. Some part of it might go
It's
up.
like
we don't know.
ballistic, right?
It's a ballistic thing. Goes up and like a ball thrown
Falls
up, and then matter comes down. So this paint also was doing the same kind of thing. And when child sees some similarity, we thought, let's find out if there is any similarity.
But how does she know what spicules look like?
Oh, no escape, because it's happening at home all the time.
She probably technically doesn't know the significance of spicules and all that, but she has seen those animations run on my laptop
and
all the
heard
time.
those terms.
So she's probably speaking like jargon and things like that. And then I just showed her that what do they look
And
like.
how did you come across this video?
So I was probably that was, I think, by accident. And then, then it of course that did strike me that perhaps there is some similarity. And then I showed it to her. And then when she said, I mean, she's like coming from no background at all. She's just a 8-year-old kid, right? I mean, doesn't know anything. She only knows some jargons. And then she said, this is looking like your spicules. So whatever she has seen on my screen. So
And
then
you were also in the beginning stages of your
even
computer simulations
computer
of
simulations,
spicules around that time, right? So then we both got excited and we said, let's look at some of the physics behind this. And that night, Piyali did some calculation on the accelerations and the ratios and stuff, and they looked quite similar.
Accelerations of?
The plasma jets there.
These are ballistic,
and
right?
here.
So then, the speed at which, so if you calculate the speed at which they go up and the time it takes to come down, so there will be some half GT square
with
kind
with
of
respect
relation.
to the gravity in Earth and compared to gravity of Sun. So we thought there might be some scaling, and they looked somewhat similar, right?
They had,
And it was quite
So
promising.
you started analyzing this
Yes.
this paint video from the...
Yes,
That's what you
I mean,
mean.
Analyzing,
Yeah?
So
Okay.
basically, you take the video, and I can see
Sure.
the frame and the time and all that, and you can do some physics and calculations.
so you were
from
just
that.
doing some simple scaling analysis, that's all. In the sun, what are the conditions here? Can we make some... Of course, they are not the same. Otherwise, if we say they are the same, people will call us.
I mean,
Yeah.
for starters,
Fools,
that's
but
plasma
yeah.
and this is
Yeah,
a
yeah.
fluid.
Yeah, of course, the systems are different.
There are
we want to make
differences.
clear that
There are
we
differences.
But there's some visual similarities.
We started with the visual similarity.
We
Then we
started-
did this scaling analysis, and then also we found some similarities. So, for example, the lifetime. What do you expect the lifetime of a spicule to be, and what is the lifetime of these jets in the
paint
lab?
jets and-
So, those also we were able to correlate when we change the conditions from the sun to the lab. We were able to, match those scales.
So it looked very promising, and we thought we'll set up something similar because it was paint, and I really don't work in a scientific lab kind of environment. We are more about teaching of science and stuff, education kind of place. So I said, this is an experiment that I can set up very quickly, and we said, why paint? Let's try to figure out what it is that will create these jets. And I tried with various kinds of fluids, bought some stuff from the market, honey and this and that.
So what is the setup? The setup is simple. Now you just have a...
The setup is actually very
Speaker.
simple. Yeah, it's a school level kind of setup. The hobbies and the popular areas are doing it. So you have a speaker, and let it be bass speaker, because bass speaker...
A big one, basically, with
yeah,
a well.
that basically responds to low frequency signals, like the bass frequencies. I think music, everyone knows what the bass, they sound like woo, woo, woo kind of thing. So these are the speakers, the large speakers, and you drive them with these low frequency signals, audio. Some music you can catch from YouTube, for instance, bass heavy music. And then you put a container on the speaker's cone and fill that container with paint. And then when you switch it on, the diaphragm vibrates, and with that the fluid also vibrates. Now the science of this, the fluid side of it was observed not on paint but on powdery stuff by Michael Faraday long time ago.
Again in 1800.
1830 or something.
I think
Somewhere.
1830s, yeah.
Yeah.
Faraday wave.
Michael
speaker
Faraday.
also.
It's called Faraday.
The bass speaker. Listening to honey
No, but
singing.
they had these drums and all, right? Large drums, so they will generate those bass frequencies. So we found nice patterns.
Faraday
Diaphragm.
did not do the... No, Faraday, I
diaphragm.
think, did not do the experiment.
No.
Faraday did the experiment himself, is
No,
it?
Faraday may not have done the experiment
Okay,
himself.
got it. As
No,
in,
Faraday did the experiment, and someone is really
No, that was again the different thing, really Plato.
it's like if you
Faraday
take a
waves.
drum and there's some dust on it and then you
Yeah,
hit it
exactly.
and it performs quite
Correct,
inside.
yeah.
Got it.
So
Like
they-
sofa jhadte time.
right.
No,
And they
this is
form
slightly
nice
different,
patterns.
though, because what we're talking there is, you're hitting a
Surface
like
and this
surface
coming
and
up.
dust coming
But this
up.
is vibrating and the dust is
There's a
coming.
fluid layer on top
There's
of
a-
what is vibrating.
Yeah.
Got it.
You're vibrating a layer of fluid.
So
No,
that
for the
is
powder
so,
experiment, I was saying.
so the
No, but the powder is on top of this.
yeah.
Fluid, okay.
Yeah, so
Yeah, so the
the
powder
drum thing,
just helps you visualize the undulations in
Okay.
yeah. So the drum thing is basically the membrane's vibrations, and some parts of the membrane vibrate a lot, some parts don't. So it's that these nodes that don't vibrate that you would find these patterns.
Just
That
looking
was
at the
Faraday.
nodes and the antinodes.
When you put some liquid, you can do that on this drum also. You can put a liquid, fill some container with liquid, and then do this. Then you can see nice wavy pattern on the surface of the fluid. So that is Faraday waves, and very fascinating. You find n number of really good videos on YouTube on Faraday waves. So that's the thing, and
Look it up, guys. Faraday waves.
Faraday
Enjoy.
waves.
Okay, next.
yeah. So this happens, and when you put some paint, curiously, these jets coming up. And when I did the initial experiment, there was no jet. It was just splashing all around here and there. So
With water.
with water, for instance, or even diluted honey or whatever. So it was still viscous, meaning it was still thick, but not.
Difficult to see the forest of jets.
Yeah, it was difficult to see all these jets coming and dropping back. So we thought there must be something in that, and we knew what it was: polymers in the paint. So then she looked up some connection with polymers and plasma and how they behave. So we latched onto that, right? And then
Yeah, so then we started, no, so the problem with the paint was we don't know what goes into making the paint, right? I mean, the paint company won't tell us how exactly they made it. And if we want to, publish a scientific paper, we need to tell that what exactly has gone into this. So then he decided to make his own polymer. And then there was a lot of, you also spoke to some of your colleagues. And
Yeah,
then
You were
it's
you
synthesizing polymers.
polymers.
You were synthesizing polymers.
yeah, so I was making all this polymer solution. I was
Polymer
basically
solution.
Polymer
making paint.
solutions.
Polymer
Yeah,
solution.
polymer
huh.
solution.
Not synthesizing the
Sorry,
polymer
yeah,
themselves.
okay.
I mean polymer
Because
solution.
polymerization and all those are now
I mean, that's
advanced,
chemistry.
advanced chemistry. So I basically bought this polymer dissolved in some solvent, and you get this solution which is like paint, except for that pigment and all the other things. So I had a controlled way of producing a polymer solution, and then investigating by.
But which polymer will work best? That took a long
Yeah, that took a
time.
long time, and there was a story. I made polarizers basically. So one of the earlier ways of making polarizers was to make something like
Polyvinyl alcohol.
polyvinyl alcohol, and
Sorry. Before you go into polarizer, what is polymer?
okay, polymer.
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 Yeah,
Oh, okay.
yeah. So basically, polymers are these. If you have one single molecule and you have an end atom that can associate with a similar atom, then another one of the same kind might come next to it, and they might join. So this bonding can continue, and these molecules, the single molecules which have these ends, which can connect to something similar, can just repeat. So this monomer, a lot of them in a chain kind of thing, would be a polymer.
And there can be like 11,000 of them.
You can
thousands
have
of them.
large chains, really
So
long chains.
polythene is just polyethane.
Is a
Polyethylene.
polymer.
Got it.
Yes,
So basically anything like certain compounds can be polymerized like this, right?
right.
Anything you can take
You
and
need these ends that can connect to similar things.
Got it.
So
It's like a Lego thing.
it's a Lego thing.
It's a Lego thing. Proteins are also
Proteins,
like
many proteins are
long
polymers.
chains. DNA is a polymer, yeah.
So plastics, there are a lot of these polymer based plastics available, and they are also stretchable.
So let me guess. Polarized polymer is a charged polymer that has
Exactly.
one negative and one positive end. No.
Not so.
No, it doesn't have. Then what does it have?
So it's interesting that they put iodine. If you put iodine in polyvinyl alcohol, then this iodine attaches itself to polymers.
Okay.
And what people did then was very interesting. They dried the thing so that it became a film like the polythene bag kind of thing, and they stretch it. When you stretch it, the idea is that the polymers, instead of being a coiled kind of mess inside, they would just stretch into linear thing. And when they stretch that, the polymer will be linear. Iodine atoms will be sitting with some bonding over there, line as a cued thing, and they absorb light in a particular direction. So light vibrating a particular direction, and that gives rise to polarization.
Wow.
So,
So it polarizes light.
that polarizes light because this preferential absorption in it will absorb one direction and not allow. It will allow light propagating vibrating in a particular direction and not allow in the other. So what I planned to do was take this polyvinyl alcohol and make these jets and see if they were polarized.
This polarized is sorry, just to ask this. Polaroid cameras use this? They do? And like the Ray-Ban polarized glasses, they use this?
Yes, same
So they
thing.
do, like, is this glass is polarized or they have layer of plastic inside it?
You can have polarized glass nowadays, I think.
Yes, you're right.
Yeah.
I mean, it's a matter of having a
Film.
film.
Yeah.
that-
Right. But I was wondering whether glass can itself be polarized.
Glass
I am
can
not
itself,
very
I
sure
don't
of that. No.
Then you have to dope it or something. like
Yeah,
that, no?
and
But
that's
still,
tricky
yeah,
because glass. There's
because
no
you
crystal
need,
structure
yeah,
or
exactly.
anything.
You need. There's
no
no
regular
there's,
structure.
There's no regular structure.
Got it, got it. You can go to polyvinyl.
Yeah.
So
this-
polyvinyl is just vinyl, but poly,
yeah,
right?
yeah, yeah.
Vinyl,
So in
it's
fact,
alcohol.
when I during the pandemic time when I did those experiments, the joke was we had this fluid on the speaker splashing all around inside
the floor.
on the house, and our flooring became polyvinyl flooring.
So we could actually peel the film off the floor
Yeah.
after
Wow.
it dried.
So after the experiment, it was a job to peel off stuff. That was pandemic time home experiments. So anyway, so this polarizing, I saw the polarization in these jets that come up. So looked like something was pulling these things. So we knew that there
Sorry,
was some
just so that I mean, you are watching this experiment
correct through polarizing
through a polarizer.
setup, and
So
observed
you're
that
trying
these,
to capture some anisotropy in.
So basically, yeah, the directionality.
Yeah.
Like I mentioned, this
That's the
polymer.
guess.
Yeah,
Yeah.
like I mentioned, this polymer sheet being pulled and made a polarizer and put on this.
Right.
Same way, the question was whether these jets that are coming out, whether they are polarized. Because if they are polarized, then there's something that is pulling them.
Those polymers
Are getting
chains
stretched.
are aligned
Wow.
along
Are
the
getting stretched.
jets.
So that was the idea. For a long time, I messed around in my head
So he
trying to
tried
design
to,
an experiment like this, but it ultimately just clicked one day.
So sorry. So you are here trying to understand why these are not breaking up,
Yes.
but are forming. That's your motivation.
Correct.
And you have somehow guessed that one
might be the
reason
polymer.
could be because the polymers.
Yes, that was holding
That's how you
things.
got to this point.
Exactly. And by the time there was some theoretical connection also to plasmas between these polymers and the plasma.
The mathematical.
The mathematical.
Yeah, we found that people have already worked on it actually from the mathematical point of view. So there are these equations which describe the polymeric fluid, the flow of a polymeric fluid, and then there are stresses, the stress strain in a fluid. So people have described the strain of a polymeric fluid. So basically what happens is these polymer chains, they back react on the fluid. So if you try to move them, so they are like strings, right? So if you pull strings, the string will try to go back to its original position. And in the process, if it is in a fluid, it will exert force on the fluid. So that is the back reaction of the polymeric chain on the fluid. So this back reaction or the stress has a very similar mathematical form as the magnetic field in the plasma. So that is another mathematical
Not
similarity.
the plasma itself, but the magnetic field in the plasma.
Okay,
Yeah.
another thing
Because
is that
when we
plasma means there is a magnetic field because there are charged particles, there are currents. So you cannot have plasma without magnetic fields, first of all. But the magnetic field in the plasma, so this magnetic field also back reacts on the charged particles in the plasma. So the charged particles are themselves forming the magnetic field, but if the magnetic field becomes stronger, the magnetic field tries to control the motion of the plasma. So there is this force and back force. A same thing happens in his
It's just like
polymers.
spring here, spring
It's just
there.
springs.
So it's basically springs stretching and stuff. So there's elastic stresses here. There's electromagnetic stress
stresses.
there, electricity and magnetism. So we wanted to design experiments that on the speaker and similar kind of simulations to be done there.
Numerical experiments
Numerical
versus lab experiments. So the numerical experiments are pertaining to the solar conditions.
You're doing magnetohydrodynamics.
Magnetohydrodynamics for solar atmosphere. So all my parameters are pertains to the solar density, temperature, solar magnetic field, whatever. Whereas the experiments that he's doing in the lab is the terrestrial,
Polymeric fluid.
polymeric.
So these parallel experiments could be like how much acceleration I should give to the speaker, for instance, so that the fluid I can see particular amount, whatever jets in a certain manner.
So we coined a new term called the forest of jets. So we said that spicules are, there are so many spicules, so we call them a forest of jets. And then we say that when we see a certain number of jets also in his experiment, we'll call it a forest of jets. So we had to define what is a forest of jet for the numerical experiment and for the
Because
lab
in the literature,
experiment.
I remember you saying back then that people hadn't gotten this forest of jets yet.
No.
They were
People wanted to find out only why one spicule is forming, or the simulation didn't have so many spicules.
But in
which
your
our
numerical
simulation had.
computer simulations, you were getting
We were getting a
lot of,
forest.
yeah.
So he was also getting a forest using a polymeric fluid in the lab, the speaker experiment.
Yeah. So then we tried to, I would do an experiment and say, why don't you do it and see what happens? And then
What are you tweaking? I mean, when you say you try, what are you tweaking in your... Here it's clear that you're tuning
but the
frequency.
same thing there.
I'm
No,
doing
what
the
do you
same
mean by...
thing there.
I mean, there's no...
Okay, so basically I have the solar atmosphere and I have the boundary. So
Photosphere boundary.
For the photospheric boundary, and I can apply any forcing to the boundary, a similar forcing that he is applying, but scaled to the sun.
Right.
And I can, crank up or down this forcing.
This you're doing on the computer.
Yes.
On the
In a
computer,
numerical
in my
model.
numerical simulation.
Okay.
And so we compared this, how much of the forcing is needed to get the forest of jets. So I can plot a curve,
Got it.
like where I have the strength of this forcing, and I have, for example, how many jets are being formed, for example. A similar thing he can do, and then we can make a phase space plot.
Yeah, so that's what is one of the figures that took a lot of time to get to. But initially we were stuck on one particular polymeric model which we thought didn't work. A lot of scientists, established ones also, were using that model and explaining things, but we were not sure whether we should be using that model because there was something I don't remember clearly.
Sorry, just to understand, you're doing the numerical model and you want to find a forest of jets in a numerical model by varying the parameters, input or whatever parameters. And you're doing the jets on a physical
Speaker.
Physical speaker.
He is an amplifier.
And you're trying to show that there is a correlation.
Yes.
There is a more like a correspondence between this system and that system.
Okay, so let's say the magnetic field, you vary by some degree and he varies the frequency of the speaker by some degree or something like that.
So that's what the phase space plot we are talking about. Okay. So we varied the frequency and the curves of these two look similar. And
so it's a plot of frequency of the driving, the frequency versus the amplitude.
Is this a high-type plot?
Yeah, sure. There can be a phase plot.
A phase plot. So frequency versus amplitude.
Oh, frequency. So speaker.
Two sine waves.
Speaker.
Both are sine waves.
Got it.
Sine
If
waves.
it's
Harmonic.
and so obviously,
at which you start seeing jets.
right. So obviously, below certain frequency there are no jets, and after certain frequency there is no jets. So in the middle, you're trying to find where is the jets,
Where is the
and you
jet?
want to see where the magnetic field, where the jets, and you want to establish that.
exactly.
Got it.
Remember that now there are two quantities here. One is frequency, the other is the amplitude of
Of
the
course, how far it goes.
Exactly.
How far
Right?
you
So
do
the
how far you
driving.
shake it,
you
right?
shake it.
Okay.
So
Driving.
you can I can shake it like this at the
Yeah.
same frequency or like this at the same
it.
frequency, right?
Got it.
So I have two parameters, and then you're asking if I have this amplitude and this frequency, what is it doing? If I have this frequency and this,
Right. Okay.
what is it doing? So
Okay.
this is what's called a phase.
And
Got
like you
it.
said,
Got it. So
yeah,
it's like, okay,
you
in
can
this
make a
area we have
boundary,
maximum,
huh?
Exactly.
optimum. What you got it.
And the boundary where the jets just start appearing will be a curve on that plot.
So above that amplitude, there will be a
There will be
forest
large
of
jets.
jets. You yourself said that, right? You yourself
I
actually
mean, I've visually seen.
mentioned that figure.
I've seen
He
the speaker
described
videos.
that figure.
Yeah, exactly. No, your
Exactly.
intuition is right.
No, I've seen the videos. There's no intuition, it's knowledge. I've seen the videos.
No, but-
so they keep varying the frequency and
Right.
they appear and
But you haven't
disappear,
seen a forest of.
Yeah, I've not seen a forest.
Yeah.
So then there is
That's
a
your
curve.
intuition.
Got it.
Right.
So then, once you establish the correspondence, then
There were a couple of more things that we did. So the idea was what is needed to create this forest of jets, because in the literature we don't see it everywhere in the solar literature, and in polymers they appear to every other YouTuber.
But nobody had done any quantitative analysis
solar.
of this. No, in polymers
in
also.
polymers also. Correct.
People have done with fluid.
Right, no,
They
just
have
to-
done Faraday
Because this
excitation,
Faraday
but not
excitation, people
polymers.
usually look at these patterns that appear on the surface.
They are
What
not
we did was
interested
we
in
said,
jets.
okay, let's look at this direction, not just the shape when you.
I mean, there are two variants of this classic. One is just with liquid, and you're saying, look at
Correct.
the spatial frequency pattern.
Right.
And the other is when you throw in a fluid like cornstarch or something, right? And
Right.
then you get. Have you seen these videos where people have thrown
starts
cornstarch
dancing.
onto a speaker?
Yeah, it takes these weird shapes.
It takes all
and
these
then,
weird shapes. They start.
They're
to
not
call it-
jets, but
They're not jets.
They're not
So you're
jets.
saying it's important somehow to have a
Yes.
polymer.
Yes, but this cornstarch thing is a little interesting in terms of fluid, the basic fluid behavior also. We have fluids like water that behave nicely. The viscosity is constant, the thickness. But there
Newtonian fluids.
Newtonian fluids.
Newtonian. And then there's this cornstarch, which is like you try to push it slowly and your finger can go as deep. It's like dal kind of thing. And then if you try to punch it, then it shows resistance.
Right.
And the second kind of fluids are like the ketchup. So you try to invert it, it won't come. But when you squeeze it, it just flows, right?
for example,
Through
even
the
paint, you
fines,
try
whatever.
to paint a wall. So when you use your brush to apply stress, it spreads easily, right?
So this other kind is what we were interested in.
So we
And
were
the
interested in
polymers,
paint, not
this
cornstarch.
thing came in.
So these are fluids which are
Sheer.
unlike water. Yeah, I mean water just flows. Depend. These are fluids which are called
The thickness
shear
varies.
responsive.
Got it. So then you found a correlation or a correspondence.
Yes. So the thing is, with water, if you did the same kind of thing, you won't see jets ever. You will just see droplets.
That's
So-
what this crocodile mating.
That's this
Thing.
crocodile mating thing that we're talking about. So they're also these alligators, not
Alligator,
crocodiles.
yeah, alligators.
So they, as part of their mating rituals, the male alligator comes and forms a kind of dimple with its back, just submerged in water, and then vibrates its back, just like the speaker thing.
It's basically singing at around 20 hertz frequency.
Yeah, at about 20 years. Or so. And then the water starts dancing on it, and it's attractive to the female alligators.
Wow.
It's attractive to us also, scientifically. So
Basically, the water is splashing everywhere.
it's water. It's just
it's
splashing.
just water.
So we don't see jets.
That is Faraday excitation in nature. But that video you digged out from this
I did.
BBC.
Anytime when you're doing experiment, any alligator came?
we-
One just starting solar flare, two alligators have come.
alligators will come.
Yeah, on the screen. On the screen, yes.
Yeah, we didn't have to go and catch an alligator.
Thankfully. Are there alligators in India? Crocodiles.
Crocodiles.
Maybe crocodiles. Maybe they do so, I don't know.
I don't know. So one of the things that we found out was you need this polymer chain to keep the jet alive, intact, and not break up into these water droplet kind of thing. So by the end of it, we could find some very. Our goal was, as people from physics, trained in physics, our goal was to find out commonalities between these two, and we said our assertion. One of the assertions that we made was. There are 4 ingredients that are required to get this forest of jets in a fluid. And one of them is directionality. One is you need gravity. You need a fluid, you need gravity, and you need directionality. And
This driving,
driving.
quasi-periodic driving.
So
directionality
directionality.
in the X-ray.
Because this
No,
excitation is
excitation.
directional. So the jet
The directionality of the
Polymer.
polymer.
Yeah,
Because
that's
of the
right.
polymer.
Exactly. So you have an anisotropy of the fluid.
of the system. Yeah.
Yo,
the
excuse
system.
me, what is an anisotropy?
This is the so when you're exciting water and this polymer fluid both by the same kind of excitation, and both directions are the same. But water doesn't have its own direction. Molecules are like oriented any which way. But over here, the polymer chains, when they go into jets, they will align along the jet.
Right.
So imagine a fluid that's comprised of marbles.
Right.
Imagine marbles. So marbles are spheres,
Ah.
right? So a fluid that's comprised of marbles has, I mean, this direction is the same as that direction is. But now imagine a fluid that's comprised of
Ladders.
Now you attach those
Or-
marbles with chains.
or
for
spaghetti.
example.
Ah, okay.
noodles,
Exactly, yeah.
noodles,
Spaghetti,
right?
huh.
So now, if I have a fluid that's comprised of noodles, the direction along the noodles is different from the direction orthogonal.
No, you will be able to see this when you actually make it flow.
Yes.
And
Right.
flow is important. So in the vessel where you cook the pasta, spaghetti or whatever, you will see that they're all tangled and any which way, right? But when you try to strain it, the strands align along the flow.
Wow.
So this is what I was trying to.
This is the anisotrope.
This is
This is
anisotrope. It's anisotrope.
Got it. Got it.
And then the forcing. We said this forcing is required, and here the forcing is very obvious on the sun.
So there, sorry. So even before the forcing, the anisotropy in the sun comes because of
Because of the magnetic field.
So magnetic field already gives a direction.
Magnetic field will give it a direction. Actually, what happens in the sun is, okay, inside the sun, the pressure of the gas or the plasma is much more than the strength of the magnetic field. So there, the gas will tell the magnetic field what to do. Whereas if you come out of the sun into the sun's atmosphere, the thing is opposite. So there the magnetic field is the master. It will tell the gas what to do. So the gas will follow the magnetic field. And then I mean in school we have seen that we have studied about this cyclotron motion, right? You have magnetic field and a charged particle spirals along the magnetic field. Exactly such a thing takes place in the sun also. So there the magnetic field orientation determines, so the solar wind direction is determined by the direction of the magnetic field. But by looking at, which way the plasma is flowing, it is possible to, visualize, okay, this must be the direction of the magnetic field. So that is what is the beauty of this, the solar atmosphere, where the magnetic field is much more stronger than the plasma itself. Like I mentioned, the density is very less, right, compared to water. So there the magnetic field is very strong.
So you like an entire understanding of how polymers work on top of speakers also aligns with the
polymeric fluids.
polymer fluids,
Not just polymers.
anisotropic, isotropic.
Anisotropic.
Yo,
Yo.
yo, what's up? Faraday, watch out, bro. Okay, sorry. So, anisotropic? Anisotropic. Fluids on top of speakers behave somewhat similar to, to a degree of accuracy, similar to.
At least there is an
Analogous.
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 Analogous meaning you can use this to study that.
Which is what we hope will happen. In fact, we've shown some bit of similarity, but we went in a lot of directions, and we hope that someone will pick it up from here and
I mean,
there.
so this is a running thread in
Got
the
it.
enterprise of physics.
A running thread, like a polymer.
In the enterprise of physics, really, right? Because Newton saw an apple fall, and somehow he is able to make connection to planets. So he's saying that some phenomena that's happening at this scale is related to phenomena happening at that scale, right? And so
The
this
universality.
is this is what's called universality in physics, and that's beautiful example is this one, right? So on one hand, you have in the lab a polymeric paint being shaken on a speaker, and on the other hand, you have the sun, right? And you're somehow able to say that the underlying physics is very similar.
Might be the same. So we hope people would at least corroborate or come up with something that would say this is either good, correct or wrong or whatever.
So sorry, you were saying the directionality. We said there's this analogy between the magnetic, the anisotropy set up because of the magnetic field versus here. Then you said forcing.
Yeah, the fourth ingredient, forcing. It's like the beer purity law of 4 ingredients. So we also have 4 ingredients.
Yeah, the forcing is the
Over
the
here it's
amplitude of the music,
Okay.
It's like
the intensity of
how
your
hard,
music, how loud it is,
how
Volume.
hard,
the
how
loudness, the volume. Yeah.
not just that, it's the, if you can plot it as a wave, it's the shape of the wave also. So what we did experiments with were like just simple wavy sinusoid kind of wave, but you could also add these and then get this music kind of thing, right? So the forcing, we said you need a kind of a periodic forcing, and
Quasi-periodic.
we call it quasi-periodic. And there also we found that the forcing is coming from the photosphere, or our
In the sun, in the case of the
simulations.
sun.
This is what we did, and we said that's
Yeah, because the sun, the
produces sequence.
surface of the sun actually vibrates.
What?
Yeah, it produces music.
What?
So, yeah, I mean, I can show you this, or I can send you audio file of suns singing.
What show?
so
we ran the
We
fluids
ran the
on that
yes,
music.
yes,
What?
yeah, that's right.
On the
Sun's music.
But that
Sun's
sun's
surface
music is actually in millihertz, so it is like 1,000 times smaller than what human ears can hear. So
speed it up.
what he did was he
just scale it
speeded
up
up.
properly.
So he speeded
scale
it up,
everything.
Very
scale
Fourier
everything.
scaling.
Insane.
So those modes are
and
actually
you're able to form jets.
we found
Yeah,
jets.
yeah.
Okay.
Yeah.
Okay.
Yeah.
Okay.
That forms.
So that movie that you saw, that was actually being driven by this music of the sun, which has been speeded up, say 10,000 times or something like
It was
that.
fun.
So, and then we had a forest of jets.
Wow. Amazing. So the moral of the story is everybody should watch YouTube videos. That's
Yes.
the moral of the story. If
It's
you're not
not that
watching,
bad.
yeah. If you're not
And
watching,
build your own experiments.
yes.
Yeah, don't
Oh.
don't just
And
keep
talk to a
watching.
scientist.
I think mostly just watch YouTube videos. It's best.
His videos.
Yeah. Our videos.
Our videos.
Yeah. All the videos, this podcast, like that. So, analogy is established, right?
We hope. We have.
So it's published now.
Yeah.
Oh yes.
So after publishing, it's done now, no?
Publication is only the
not
start
really.
of.
Yeah.
You have
It's
to
only the
disseminate.
start of the
You have to
discussion, right?
disseminate.
Yeah,
You
and
have
then-
also have to convince people.
And then science nowadays is done at various levels as
Just we are all humans. Scientists are also humans. Our interactions are also, So there are groups. There are closed groups. There is a lot of, the social structure among scientists as well.
we are
So-
nothing. Planck said science progresses because people with old ideas die, new people come. Or something like that. Max Planck.
Shashi, time to go. But
I'm not even a scientist.
it's too long.
I'm not
We're
even a
alive for too long, Shashi. Sorry. Guys, please RIP Shashi in the comments. Okay. So what is the future for this project? Are you doing more on it or what are you doing?
we had a lot of plans.
We had, there's lots of threads. First of all, this Faraday oscillation and how this jets start developing, the dynamics of this jets to start developing. That is very beautiful because over here we can start and see the development. In the numerical, we can do that. On the sun, you can't start them. They're already there and it's happening all the time. So here it was very nice, and one could proceed and find out what is known as the dynamics chaos or whatever that regime is, nonlinear
Descent to
dynamics
chaos.
of it, and then descent to chaos. Then there are other
These
things
waves,
like these
killer,
4
what are these?
ingredients that we've talked about. Are they really so sacred as we think they are, and as it appears from our study? So that's something. Of course, this is also this is not a theory. This is an analogy that we've shown.
This
And
4 ingredient criteria
yeah, and how
of
spicules
jets,
form.
forest of jets.
So we hope people can further this work and establish it, or we'd like to know if we are wrong. So
But
either
do
way.
you think that there could be things that you're learning from your tabletop experiment which might give rise to observations on the sun which may not, spicules, of course, it came the other way. You know that there is a structure like spicules, and then you're looking for an explanation for that. But do you think there might be features that this throws up which might provoke going us
Correct.
to looking at the sun and finding something
So
new
we
there?
have done
For
2D
example, the
simulations for
twist,
this.
the
Yeah. So
twist,
we have done 2D simulations here. When you go to 3D, you see much more dynamic effects, like you see on those YouTube videos, things twist and stuff like that, that we cannot see in the 2D simulations that we presented in this work.
Nor from the data from the sun.
From the data, we see some evidence of twist, but the data is as good as the resolution, as good as the instruments we have.
No, but this is not a phenomenon that's been identified
Clearly
and
established.
articulated
No,
so
no,
far.
Clearly.
no.
Okay.
There is
That's
some.
an
There are some
interesting-
signatures of the spinning twists and things like that.
Chirality.
And
It's an emergent
chirality, and some of those things we found when he did experiments with 2 different paint colors, for example. So you would see this the 2 paint threads getting wrapped around each other, producing
That was
this.
suggested by Robertus to have 2 paint colors, so that when they are twisting, you can actually clearly see the colors.
So, I mean, such a thing, for example, are known as Alfvén waves in the solar plasma context, and people. Alfvén waves are a very hot topic. So this was actually the Alfvén waves is named after Hans Alfvén, who was a Swedish physicist who got a Nobel Prize for this, not discovery, this theory of Alfvén waves. So these Alfvén waves are very important because they may play a role in again heating the corona. So people want to detect these Alfvén waves, and what best place to detect them is the spicules. So this twist or whatever that is occurring, maybe because of these Alfvén waves in the solar plasma, but we also see it here because of Faraday waves.
You also
So
thought
that
if
may be
people
something.
could get close or high resolution or better spectral resolution, meaning
Spectral resolution,
color-wise or wavelength-wise resolution, then people, meaning we could correlate it with your
Yeah, also there was one more similarity that we did not explore. That was, in our 3D simulations with, my former PhD student, Shohel. So he found that these spicules are not actually like 1D conical jets, but this is like a curtain, like a, drapery curtain, like a folded curtain. And you always see them as jets because, when you're looking at an image of a sun, it is a 2D image of a 3D object. So you are basically summing over the light that is coming along your line of sight. So in the 3D simulation, we found this curtain-like structure, and when we, this kind of a pleated drapery kind of a structure. So when you just integrate the light coming out from that structure, you actually see these jets. And in his experiments also, especially during this nonlinear development,
Yes,
this
during the
starting
beginning of
phase,
this.
What are called these labyrinthine waves.
these
Crispation
kind
is
of
what-
crispation. So we could see this wall of paint rising, and then they're forming these jets. So that we have not explored. So what is there any connection or not? Because that is also new. Because people ask us that why don't you actually see it on the sun? So we are basically saying that we don't see it in the sun because we don't have enough spectral resolution, or not spectral. We don't have enough intensity resolution, or we don't have enough spatial resolution, so we don't see it. Or we need some stereoscopic vision to look at the same region of the sun. We don't have that technology right now, so we are not able to observe it. But that doesn't mean it's not there.
But also this fluid thing itself is interesting. There are these areas, known areas where many times the waves form squarish kind of patterns, and you find them on YouTube also. People who visited those places from those lighthouses.
Yeah,
and
some
all.
France, I think there is some
Yeah, there's
place
one place
like
in
that,
France or
right?
Italy, I forget. And in one of my experiments, I took a square container and started these jets, and the pattern looks exactly same. It's supposed to be dangerous to go to because I
Yeah,
think
rogue waves or
they're
killer waves,
you
they
get
are called.
confined to that square cell. You can't, because normal waves you'll get blown to the shore or something like that. There you're confined.
Got it.
It's a very interesting connection actually that could be explored.
Wow. Got it. So a lot of work still to be done, basically, is what I'm understanding.
Yeah, even if it is
A
not
lot
as-
of work that can be done.
Can be done.
Can be
Okay.
done.
Can be done. And like this is a start of a lot of possibilities, basically.
I would want to then continue a lot of this stuff.
Tabletop solar fluids.
Solar, yeah, solar.
Got it. Don't watch more YouTube videos. One has taken you into deep dark forest objects.
Yes.
Okay, great. But thank you so much for
Yeah.
coming and sharing with us this very fun experiment. It's a fun experiment at the end of
Yes.
the day.
A lot
Yeah,
of
it
fun.
was a lot of
All
fun
experiments
actually.
are fun experiments.
Excuse me. Okay, hopefully so. Yeah, so thank you for sharing this fun
Yeah,
experiment
thank you
with us.
for having us.
Thank you.
Yeah, hopefully everybody got to learn something from this, either about the sun or about the fluids or about how generally science works, etc. Like, share, subscribe. This episode is available both on my channel and on Azim Premji University's channel. I don't know which one you're watching on, but whichever one you're watching, go to the other channel and subscribe also. So that's all I care about. Thank you so much, and bye-bye. Everybody say bye to the cameras. Hello, bye,
Thank
bye,
you.
bye, bye, bye,
Thank
bye,
you.
bye, 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 bye.